Before sunrise, while most cities are still dark, millions of eggs are already moving. They roll out of vast poultry houses and onto long conveyor belts. They pass through tunnels of light, spinning brushes, warm water, cameras, scales, robotic arms, printers, and packing machines. The entire journey can take only minutes. But inside those few minutes, every egg faces a silent test. A crack thinner than a human hair can destroy it. A hidden blood spot can remove it from the food chain. Temperature mistake can increase the risk of dangerous bacteria. And one failure in a factory processing hundreds of thousands of eggs every hour can affect stores, restaurants, bakeries, and homes across an entire region. From the outside, an egg looks simple. Inside the processing plant, it becomes one of the most fragile products in modern food manufacturing. So how do factories clean, inspect, grade, weigh, stamp, and pack millions of eggs without breaking them? And what happens to the eggs that never make it into a carton? The answer begins far from the supermarket shelf. It begins inside a building that never truly sleeps. Long rows of laying hens fill the production houses. Depending on the farm, the birds may live in cage-free barns, enriched housing systems, free-range systems, or other commercial environments. Their housing changes from country to country and farm to farm, but the industrial mission remains the same. Collect the eggs quickly, keep them clean. Protect them from damage, move them into controlled processing. A hen usually lays an egg into a nesting area designed with a slight slope. Gravity then takes over. The egg rolls gently away from the bird and onto a narrow collection belt. Its small movement is more important than it looks. The moment the egg leaves the nest, the race against time begins. Its shell appears solid, but under a microscope, it contains thousands of tiny pores. Those pores allow gases and moisture to move through the shell. Over time, the egg slowly loses water and carbon dioxide. The air cell inside becomes larger, the white becomes thinner, the yolk becomes less stable. Freshness is not a permanent condition, it is a countdown. Several times each day, the collection belts begin moving. Thousands of eggs emerge from different rows and merge onto a larger conveyor system. First, the flow appears chaotic. Brown eggs, white eggs, slightly dusty eggs, perfectly clean eggs, large eggs, tiny eggs each, moving forward without a carton or label. But hidden beneath this moving river is a carefully controlled system. The conveyor speed must be fast enough to handle the far mass production, yet gentle enough to prevent collisions. Eggs are strongest when pressure is spread evenly across the shell. They are much weaker when struck at one small point. That means a harmless-looking metal edge, a damaged roller. Or one egg arriving at the wrong angle can trigger a chain reaction. One cracks. The liquid leaks. Nearby eggs become contaminated. The belt becomes dirty. And suddenly, a small mechanical problem becomes a sanitation problem. To prevent this, modern systems use smooth transitions, soft guides, carefully spaced rollers, and sensors that watch the flow. Some facilities process eggs in a grading plant connected directly to the laying houses. Others collect the eggs onto plastic trays or flats and transport them to a separate facility. In an inline operation, the eggs may travel from the hens to the processing equipment without being manually handled even once. That is the first major secret of high-volume egg production. The safest hand is often no hand at all. Every time a person touches an egg, there is a chance of dropping it, cracking it, warming it, or transferring dirt. Automation reduces those risks, but it also creates a new danger. When machinery moves this quickly, one failure can damage thousands of eggs before a worker even sees the problem. So the factory watches everything. Sensors monitor belt movement. Control screens display production rates. Workers patrol the lines, listening for unusual sounds. A change in vibration can reveal a damaged bearing. A pileup can mean a blocked lane. A sudden increase in cracked eggs may point to a transition that is moved by only a few millimeters. In this factory, sound is evidence, and the experienced workers know what the machines should sound like. The eggs now approach the first transfer point. They enter the processing room in irregular positions, but the equipment needs order. Special rollers separate them into individual lanes. Mechanical guides adjust their spacing. The eggs rotate as they travel, allowing the machinery to examine nearly every part of the shell. The line is no longer a random river. It has become a formation. Each egg now has its own position, its own path, and soon, its own electronic record. But before the factory can decide where an egg belongs, it must deal with what may be on the outside: feathers, dust, dried organic material, and microorganisms too small to see. In many large commercial operations in the United States, eggs are washed before grading and packing. The rules and exact practices differ internationally. In some countries, table eggs are commonly sold unwashed to preserve the shell's natural outer layer. In the United States, commercial washing and refrigeration are central parts of the system. The washing process looks simple. It is anything but simple. The eggs move beneath controlled sprays of warm cleaning solution while rotating on rollers. The temperature matters. Chemistry matters. The water pressure matters. Even the direction of movement matters. If the wash water is too cool compared with the egg, the contents inside can contract. That pressure change may encourage contaminated moisture to move through pores or tiny shell defects. The goal is to clean the egg without driving contamination inward. For that reason, commercial systems carefully control washing conditions. Dirty water drains away instead of being allowed to pool around the product. The equipment itself must also be cleaned because a washing machine can either remove contamination or spread it. That is the uncomfortable truth inside every food factory. Sanitation system only protects the product when the sanitation system is itself kept sanitary. The eggs continue forward, wet and shining. Now, powerful air blowers remove surface moisture. Drying is not merely cosmetic. Moisture left on the shell can create handling problems, weaken packaging, attract dirt, and support the movement of microorganisms. The air knives force water away while the eggs continue to turn. For a few seconds, the line disappears behind a storm of spray and air. Then the eggs emerge, clean, dry, and ready for the part of the factory where their hidden secrets are exposed. The lights ahead are not ordinary factory lights. They are part of a process known as candling. The name comes from an older method in which eggs were once examined in front of candlelight. Today, industrial candling systems use powerful lamps, optical sensors, cameras, and computer analysis. As each egg passes over or in front of the light, the shell becomes partly transparent. For an instant, the machine can see what the human eye cannot: the air cell, the yolk shadow, the condition of the white, unusual internal material, certain shell defects, and signs that the egg may not belong in a consumer carton. USDA grading guidance explains that candling is used to assess internal characteristics, including the apparent condition of the yolk, white, and air cell. Final quality grades are based on both shell condition and internal quality. A high-quality fresh egg usually has a relatively small air cell, a firm white, and a yolk that remains well-centered and less visible during movement. As the egg ages, the white becomes thinner. The yolk may move more freely. The air cell grows as moisture and gas leave through the shell. None of this requires the shell to be opened. Light tells the story. But the machines are not only judging freshness, they are hunting for danger. A cracked shell can allow bacteria to enter more easily. Some cracks are obvious. Others are almost invisible. These are known as hairline cracks or checks. To find them, factories may use electronic crack detection systems that gently tap the shell and analyze the sound or vibration produced. A sound shell responds differently from a damaged one. The difference may be impossible for a worker to hear over the factory noise. To the computer, it can be unmistakable. Each egg is lightly contacted at several points. Sensors capture the response. Software compares it with expected patterns. Then, before the viewer could blink, the egg is either accepted or marked for rejection. The strange part is that nothing appears to happen. The egg keeps moving beside all the others. But inside the control system, a decision has already been made. Farther down the line, a mechanical gate or suction device will remove it. This is where the factory's hidden intelligence becomes visible. The conveyor may look like one continuous stream, but the computer sees thousands of separate objects. Egg number 41,286 may be medium weight with a clean shell. Egg number 41,287 may have a hairline crack. Egg number 41,288 may be extra large. Egg number 41,289 may contain a detectable internal defect. Every decision must follow the correct egg as the line moves at high speed. Lose track of that position for even a moment, and the wrong egg could be packed while the good egg is rejected. So the machine builds a moving digital map: position, weight, shell status, quality result, destination lane. All of it travels with the egg through the system, even though the egg itself carries no visible identity yet. Then comes another test: the scale. Consumers often talk about large eggs or medium eggs as though the categories describe appearance. They actually describe weight classes. An egg may look almost identical to the one beside it, yet belong in a different carton because of a difference of only a few grams. Industrial graders weigh eggs individually while they continue moving. There is no long pause. No worker places each egg on a kitchen scale. The equipment measures the load at speed, sends the result to the central control system, and assigns a destination: small, medium, large, extra large, jumbo. The exact class names and minimum weights depend on the market and grading standard. The machine does not care whether one egg looks impressive. It cares what the sensors report. Any eggs caught in an unsafe area must be assessed. Restarting requires more than pressing a button. The first eggs through the repaired section may be checked closely for cracks, contamination, or incorrect handling. In this world, engineering and food safety are inseparable. A loose bolt can become a contamination hazard. A worn roller can become a breakage problem. A failed refrigeration unit can threaten an entire inventory. And a software error can send the right egg into the wrong package. This is why the quietest moments in the plant may be the most tense. When the belts stop, workers notice immediately. The endless rolling sound disappears. Warning lights flash. Supervisors look toward the control screens. Somewhere inside hundreds of meters of machinery, the flow has been interrupted. The question is not only what broke, it is which eggs were affected. Once production resumes, the factory begins moving again with the same strange combination of force and delicacy. Steel frames shake, motors hum, pumps move water, air knives roar. Robotic arms swing through the air. Yet at the center of it all is an object that can crack against the edge of a bowl. That contradiction defines the entire operation. Heavy industry built around extreme fragility. The factory does not make the egg. The factory's job is to protect, evaluate, organize, and preserve what already exists. And despite all the technology, nature refuses to produce identical units. Every shell has a slightly different shape. Every egg has a different weight. Every yolk sits differently. Some shells are stronger, some are thinner, some are spotless. Some arrive carrying evidence of the environment they came from. Manufacturing usually begins with standardized materials. Egg processing begins with biological variation. The machines must adapt to nature at industrial speed. That may be the greatest achievement inside the plant, not that it moves millions of eggs, but that it treats each one as an individual long enough to decide its fate. One becomes part of a breakfast. Another becomes a cake. Another becomes liquid egg for a restaurant. Another becomes dried powder shipped across the world. Another is removed because of a crack no shopper would ever have seen. By the time a carton reaches a refrigerator, the violence and precision of the process have disappeared. There's no sound of rollers, no glare from candling lights, no rush of cleaning water, no hiss of suction cups, no control room tracking tens of thousands of moving shells. There are only eggs resting silently in molded pockets. They look untouched, almost ordinary. But each one has survived a journey through one of the fastest and most carefully controlled food processing systems on Earth. It has been moved without hands, washed without being flooded, examined without being opened, tapped without being broken, weighed without stopping, tracked without a visible number, lifted by air, packed by robots, protected by refrigeration, and delivered through a chain in which a few degrees, a tiny crack, or a few seconds can make the difference between acceptance and rejection. Some facilities process eggs in a grading plant connected directly to the laying houses. Others collect the eggs onto plastic trays or flats and transport them to a separate facility. In an inline operation, the eggs may travel from the hens to the processing equipment without being manually handled even once. That is the first major secret of high-volume egg production. The safest hand is often no hand at all. Every time a person touches an egg, there is a chance of dropping it, cracking it, warming it, or transferring dirt. Automation reduces those risks, but it also creates a new danger: When machinery moves this quickly, one failure can damage thousands of eggs before a worker even sees the problem. So the factory watches everything. Sensors monitor belt movement. Control screens display production rates. Workers patrol the lines, listening for unusual sounds. A change in vibration can reveal a damaged bearing. A pileup can mean a blocked lane. A sudden increase in cracked eggs may point to a transition that is moved by only a few millimeters. In this factory, sound is evidence, and the experienced workers know what the machines should sound like. The eggs now approach the first transfer point. They enter the processing room in irregular positions, but the equipment needs order. Special rollers separate them into individual lanes. Mechanical guides adjust their spacing. The eggs rotate as they travel, allowing the machinery to examine nearly every part of the shell.